So for the second part of this demo, what we're going to want to do is remove this AC voltage source, and we're going to replace it with a sinusoidal voltage source, V sine. I'm going to put that right in where our AC source was, hit escape to stop placing, and let's set our offset to 0, so we don't want any DC component. Let's set our amplitude to 1, so it'll be easier to recognize some key values later on. And we're going to manually adjust this frequency and do several simulations. So let's start with a really low frequency of 1 Hertz. And we're just going to leave the AC alone. So, of course, I'm choosing a low frequency because this is a low pass filter. So what we expect is for our output to be essentially unchanged from our input. And that's because this frequency is much lower than the corner frequency, which we have confirmed in the previous video to be our 118 Hertz. So what we need to do now is we need to create a new simulation profile. So let's call this our transient response. So let's get rid of, so it's not liking my punctuation, so let's do that. And so anytime we're wanting to plot something over time, we're going to use this time domain or our transient. And so since we're going to be adjusting these frequencies to a few different values, let's sort of standardize the settings here. So let's say we want to see 5 periods of data regardless of frequency. So in this case, if our frequency is 1, our period is also 1 second, which means 5 periods would be 5 seconds. Similar thing down here, let's try to get a standard for our maximum step size. And so that's just going to help ensure that we have the same resolution in all of our plots. So let's arbitrarily say that we want the maximum step size to be the period divided by 100. So in this case, if we have a period of 1 divided by 100 is going to give us 10 milliseconds. So let's set that up and let's run our simulation. So again, because this is a low pass filter, this low input frequency we would expect to be passed to the output with no issues. So we would expect our input and output to essentially look the same. So let's see if that's true. So coming over here, we're going to plot, and again, remember I can sort of clean this up if I know I'm looking for voltages, deselect currents and power. Let's plot our input and output on the same plot. And as expected, we see our red and green curves, so green is our input, red is our output, are essentially right on top of each other. We see that the peak value is 1 volt, our negative peak or our lowest value is -1, and our period is 1 second as expected. So essentially no difference. We could maybe zoom in, see if there's a little difference. So let's maybe just zoom in right here. And so we can see zooming in, maybe there's some slight differences here and here, but really from that high level view, it's pretty much looks the same. Okay, so now let's adjust this frequency. And so we've seen what happens for a frequency that gets passed, but now let's see what happens for a frequency that's really large. So let's try 1.2K. And so by large, I mean large relative to our corner frequency. So remember, we confirmed our corner frequency, our other names for it are 3 dB frequency, to be 118. So this value is over 10 times that. So we need to also adjust our simulation settings though. So let's adjust this to be 5 periods. So for 1.2 kHz, that corresponds to 4.2 milliseconds. And we're going to stay with that arbitrary maximum step size of period divided by 100, which gives us 8.3 microseconds. So let's click OK, and let's rerun our simulation. All right. So in this case, what we would expect is we would expect for our output to be a lot closer to 0 and to not look like our input really at all. So let's plot our input and our output. And again, our input is green, our output is red, and so we see this is pretty much what we expected. So for our input, we see it's still oscillating between 1 and -1, so we just have this sinusoidal wave that's constant, but now our output is much smaller. We see if we sort of zoomed in, we could still see some sinusoidal action going on there, but with the magnitudes here, it's kind of hard to see. So let's see if we can't maybe zoom in right there. And so there we can see it still has the basic sinusoidal properties, the same period that we have for our input waveform, but it's hard to see on this plot, and we'll see it in the next one, but basically we do have this output waveform being shifted to the right in phase. And so if we were to increase the frequency further, what we would see is that this red output curve would just be getting smaller and smaller and closer to a value of 0 as that gets blocked more and more effectively. So now let's come back and look at one final frequency value. And let's take a look at 118 Hertz, so our 3 dB frequency. And so again, we're going to need to update our simulation profile. So we want this to be 5 times the period. In this case, that is 42 milliseconds. And we want this maximum step size to be our period divided by 100, which again, we arbitrarily chose, and that is 85 microseconds. So let's update that and run our simulation. Okay, so again, we're going to plot our input and our output on the same plot. And so here we kind of see it's sort of an in-between. So our green input and our red output, so we notice our input hasn't changed, so it's still going between 1 and -1. However, our red, it's noticeably decreased, but certainly not to the extent that we saw with the 1.2K where it was down here. So we have seen some decrease, and we also see this phase shift, which is a value that we identified in the previous video. So this phase shift would be the difference in the angle between here and here. So if we want to get some more detailed information from this plot, what we can use are our cursors. So I'm going to click here to toggle the cursors on. And so notice by default, we have 2 cursors, 1 and 2. Right now, both of them are on the green curve. And we're going to come back and adjust that in a little bit, but for now, let's just focus on one cursor. So notice, so I'm going to use my arrow keys on the keyboard. I can move this cursor to the left or to the right along this green curve. So I'm just holding down left or right at the moment to move that cursor. I can also left click at any point, and it's going to take the cursor to that spot on the green curve. So notice even if I click up here, it's going to go to the spot on the green curve where that corresponds to in time. There's a lot of nice cursor functionality up here. So for instance, if I want to find the peak, I can find the peak value. So it's shot my cursor right there. And coming down here, we have our cursor information. So as we would expect, our value is 1 at that point. Okay, so let's look at our second curve. So if we want to move this red cursor to our red curve, what we can do is we can come down here to these markers, and I can left click on the marker for my output. And so what that's going to do is move that to my red curve. So let's say we want to know the peak value here. So I'm going to click peak. And so it's jumped over here because that was the one sort of next up. And so we can see that is a value of 716 milli. So right down here in the bottom. Again, kind of difficult to read. But what that's telling us is that we have 0.716 millivolts at our peak value. And as you'll notice, this peak value is not very consistent throughout. So if we let this run longer, it would become more stable. But we sort of have this transient upstart where our capacitor and inductor were not fully charged. So that's why we have sort of this different peaks at the start and then decreasing and then increasing. But this 0.716 is approximately what we would expect in terms of having the value at our 3 dB frequency be 1 over root 2 times the input. So 1 divided by root 2 times 1 gives us 0.707. So again, if we let that response go longer, we would see that getting closer to 0.707 or 707 milli. So another thing that can be useful, so let's say we want to keep this cursor on our red curve. Well, we actually have a second curve as well. So our second curve or second cursor is actually on our green curve. And so I can move that one around by holding down shift and using my arrow keys. So holding shift, I'm hitting right arrow key, and we see that's moving the second cursor along my green curve. I can also right click anywhere, and that's going to move the blue cursor to that point on the green curve. I can also reassign these. So let's say I want the blue cursor on the red curve as well. So if I come down here and right click on this marker, notice my cursor 2 is now moved here. So I'm going to right click on the input to move it back to the input. For instance, maybe one thing that we're interested in is the difference between these peaks. So what I can do is get this over here close to the peak, and I can click on this. So I'm left clicking up here, and because I was moving my blue cursor last, it's performing that action on that. And what we can see here is we can actually see the difference between some of these values. So in this column, we have cursor 2. We can see our green curve is 1, our red curve is at negative 0.567. Same thing, we have both of these values for cursor, our red cursor. And then over here, we have the difference between our y values and the difference between our x values. So we have that our x value is 3.48 milli, a difference. And so that checks out with what we see here, so about 3 milliseconds. And then we can also see the difference between our two values as well. So that's how we can use our cursors. And then of course at any time we can turn our cursors off if we want to see a little bit cleaner plot. So let's go back and see if we can't run this a little bit longer to see if we can stabilize that. So what I'm going to do, if we see it, let's see if we can get that a little closer to our 0.707. So let's run this a little longer. Let me run this, let's just go ahead and say to 500 milli. And then let's say we don't want to start saving data until after 100 milli. And hopefully that's going to give us enough time. Right, this should just be 1M. What that's going to do is hopefully that's going to sort of pass that initial transient startup, and we'll see a little more uniform peak for our output voltage. So let's take a look at what this looks like. So input, output, and we're going to have a lot more periods here. So let's maybe zoom in on some of this out here. So it's just got upset with me for clicking poorly. So let's zoom in out here a little beyond 450 milliseconds. And so just right away, we can see that this looks a lot more uniform. So let's go ahead and click on our cursors, and let's put that right there. And so again, I need to assign these to my red curve. And peak value we see is 708 milli. So we're definitely trending closer to that expected value of 707 milli.